Night falls like a page turning. A leaf loosens, spirals, and never climbs back to the branch. A star spends its youth in fusion's bright arithmetic and will not unburn its light. A child's footprint in wet sand becomes a blurred memory, then nothing at all. Across oceans, deserts, and cold interstellar gulfs, the same one-way current is felt. Warmth thinning into chill, order relaxing into scatter, the crisp edge of now sliding into the soft distance of before. Space can pause, hold its breath, seem almost still. Time does not. Its river carries galaxies like seeds, grief like weather, and thought like flicker. Clocks only count the drift. They do not cause it. Equations whisper symmetry, yet teacups shatter and do not leap whole from the shards. The universe keeps records in ash, not in reversing. Heard through radios and telescopes, the cosmos hums with afterglow. Light stretched thin from a young, blazing fog. That glow remembers a hot beginning. It does not foresee a return. Gravity gathers, stars ignite, black holes warm the void with the faintest breath, and everything that can forget eventually does. Still, the deep laws, Newton's neat steps, Maxwell's ripples, Schrödinger's elegant spiral, permit a dance in either temporal direction. The stage welcomes reversal. The performance never chooses it. So the central riddle stands, steady as a North Star. Why does time only move forward? Why do the foundations of physics admit a mirror world that nature refuses to perform? From steam to starlight, from memory to mathematics, the answer hides at the seam between initial conditions and unfolding fate. To seek it is to walk a bright edge between certainty and wonder, to listen for an arrow that aims through every heart and every horizon, and ask who drew the bow. Steam lifted from the mouths of iron machines like breath in winter air, and the 19th century learned to count it. Along rail lines and river banks, pistons hammered out a furious rhythm, coal embers glowed, and industry discovered that warmth could be domesticated but never fully tamed. In 1824, Sadi Carnot, a quiet analyst of engines and limits, described a world where heat climbed down a staircase of temperatures, and where no clever arrangement could surpass a fundamental ceiling of efficiency. His ideal cycle, traced on paper more elegantly than any wheel could manage in steel, implied a principle harsher than friction. Even a perfect engine must spend potential like a currency that cannot be earned back. Temperature differences powered work. Equality brought rest. Beneath the smoke and soot, a deeper order was being sensed, one that ran not on gears but on direction. Rudolf Clausius gave that direction a measure. In the 1850s, he shaped the second law into a sentence that would haunt every kettle and comet. There exists a quantity, the entropy, for which the total tends to increase. He whispered mathematics into irreversibility, and the whisper could not be unheard. Lord Kelvin, surveying the same thermodynamic landscape, saw farther downslope. A universe headed toward a uniform warmth so useless it might as well be cold. A heat death, where no gradient remained to push a wheel, lift a weight, or stir a breeze. The engines that lifted nations also lifted a curtain. Behind it stood a principle that did not negotiate. Irreversibility entered physics as a fact, felt in boilers, measured by calorimeters, long before it was recognized as a mystery. If underlying laws allowed motion to be rewound, why did reality refuse the rewind? Ludwig Boltzmann, restless in Vienna, sought the bridge from reversible collisions to irreversible days. He pictured a gas not as a fog but as an invisible parliament of particles, each a point pirouetting through phase space. In 1872, he wrote down an equation and a promise, the H-theorem, showing that, for a gas with momenta randomized by typical collisions, a function related to entropy would steadily descend toward equilibrium. The descent did not come from a hidden arrow in Newton's laws. It came from statistics, the overwhelming numerical dominance of disordered microstates over neat, unusual ones. He named the crucial step Stoss-Zahlensetz, molecular chaos, an assumption that precollisional velocities were uncorrelated. With that, a direction emerged from typicality, not decree. The rebuttal arrived with surgical clarity. Joseph Loschmidt posed his reversibility paradox. Flip every molecular velocity at an instant, and the same equations would run entropy downhill. If the laws permitted a rewind, what forbade it? A few years later, Ernst Zermelo, leaning on Henri Poincaré's recurrence theorem, argued that a bounded mechanical system would, given enough time, return arbitrarily close to its initial state. Where then was permanence in the slope toward disorder? Boltzmann answered with measure and rarity. The reversal required a conspiracy of initial conditions so delicate it barely belonged to the world. Recurrence would come, but on timescales so immense that star fields would change their constellations of matter, and light long before a teacup reassembled from dust. Typical gases do not collaborate for miracles. They follow the census of possibilities. A phrase gave the difficulty a shape that could be aimed at. In the late 1920s, Arthur Eddington spoke of the arrow of time, and a loose collection of dilemmas found a single image. Entropy supplied the fletching. The arrow points where entropy increases. Radiation seemed to obey the same targeting. Retarded waves spread outward from sources while advanced waves arriving from the future remained purely mathematical solutions, politely absent from the sky. Even causation, never a law, always a pattern, appeared aligned. Records accumulate from what is called the past, while the future stores no libraries. The arrow was not in Newton's equations, nor in Maxwell, nor in Schrödinger's. Yet it pierced every macroscopic phenomenon like daylight through a window. Numbing it did not explain it, but it made further denial impossible. The cosmos itself then provided context, the way a horizon gives direction to a walker. In 1929, Edwin Hubble assembled redshifts and distances into a single expanding breath. Galaxies receded in proportion to how far they were. Space was not a static stage, it stretched. A universe that expands has a history, and a history invites a beginning. The arrow that carried steam into motion and gases into equilibrium might be anchored, not in small rooms of iron and heat, but across the largest possible room of all. In 1965, Arno Penzias and Robert Wilson, with a patient antenna and an unexpected hiss, heard the afterglow of a hot, dense youth. The cosmic microwave background, a bath of radiation at a few Kelvin, astonishingly uniform, sprinkled with tiny anisotropies. Predictions from Big Bang nucleosynthesis had already hinted at a furnace that forged light elements. Now the furnace's light was seen, stretched to microwaves by time's long pull. The universe had once been smoother, hotter, simpler. If entropy measures the number of ways to arrange a system without changing its broad appearance, then the early cosmos, nearly featureless in its geometry, carried a special signature: low gravitational entropy. Gravity inverted the intuition learned from steam. For a non-gravitating gas, uniformity is high entropy. For a self-gravitating field of matter, uniformity is fragile order and clumping. Stars, galaxies, black holes, explores the larger phase space. Across this landscape, a suggestion would later harden into a guiding suspicion. Perhaps the arrow's source lay in a boundary condition, a remarkably smooth early universe whose curvature, especially the free, trace-free part called the Weyl curvature, was near zero. The low entropy was not generic, it was selected. The arrow was not legislated by dynamics, it was set by the initial page of the cosmic book. Yet another frontier complicated the story, one that dealt not in steam or stars but in questions of what counts as a fact. In 1932, John von Neumann formalized quantum measurement as a two-stage ritual: continuous, reversible unitary evolution according to the Schrödinger equation, and a sudden, probabilistic projection onto an outcome upon measurement. The first stage wore no arrow, the second smuggled one in. The contrast left a mark. Irreversibility seemed to enter physics the moment observation did. Later, a quieter mechanism stepped forward. Beginning with H. Dieter Zeh and deepened by Wojciech and others, decoherence reframed collapse as a practical, though not fundamental, loss of quantum phase information into an environment. A dust grain in sunlight, a macromolecule drifting through warm air, a superconducting qubit coupled to a bath. In each case, entanglement with uncounted degrees of freedom selected stable, pointer states and suppressed interference between alternatives. Classicality, and with it the everyday sense of definite outcomes, arose not from a law that broke time symmetry, but from correlations that became untraceably distributed. The arrow reappeared as bookkeeping. Information once dispersed into countless environmental modes could be, in principle, retrieved, but in practice never was. The mathematics allowed reversal. The world, with its oceans of degrees of freedom, did not cooperate. Concrete evidence sharpened the outline. The microwave background's tiny temperature ripples, measured first by Kobe, then mapped in exquisite detail by WMAP and Planck, encode the seeds of structure and the fingerprints of an early, almost perfectly smooth geometry. The very existence of long-lived stars and sprawling galaxies testifies to gravity's appetite for increasing entropy by building islands of complexity that later darken into horizons. In laboratories, interference fringes of large molecules survive only when environments are tamed. Once reconnected to the world, decoherence times plunge and superpositions wither into records. In each domain, the same pattern repeats. Equations accommodate reversals. Typical conditions do not. The arrow resides in the improbability of coordination, in the specialness of beginnings, and in the ubiquity of environments that entangle and disperse. Thus the discovery proceeds in widening circles, from boiler rooms to billiard ball gases, from a name that fixed a paradox to a universe whose first moments were not generic, from a quantum rulebook to the fragile emergence of facts. Each circle encloses the same absence. No sign has been found of a dynamical law that commands time to move forward. Instead, the record points to selection and context. Engines reveal a slope. Statistics explain why slopes are almost never climbed. The sky supplies the initial incline. Measurement shows how local histories harden into permanence. The arrow becomes a tapestry woven from boundary conditions and typicality, from correlations that grow, and from horizons that hide. Even in this clarity, a residue remains. A calculation can exhibit typicality. It cannot explain why the cosmos began in such an atypical state that typical evolutions would generate the world known to telescopes and thermometers. Decoherence can show how quantum superpositions go silent to observers coupled to environments. It cannot say why those environments already carry the asymmetries that favor retarded echoes over advanced ones. The microwave background can outline an early smoothness. It does not settle whether that smoothness was authored by inflationary dynamics or written by a deeper rule that governs initial geometries. Discovery here is the drawing of a map whose blank regions have been moved but not erased. The chapter closes on a patient panorama. A beam engine slows, its flywheel rests. A set of molecules hurries toward a Maxwellian calm. A spiral galaxy matures, its arms crowded with newborn clusters and ancient remnants. A superconducting qubit relaxes into a pointer state as photons carry away the coherence it once held in superposition. Across scales, the same pressure toward forgetting writes the same kinds of history. The question that woke in the age of steam survives into the age of satellites and qubits. If the laws are ambidextrous, what fixed the sign on the cosmic hand? The next search will follow the trail from evidence to edge, testing whether the arrow is anchored in gravity's entropy, in the smoothness of birth, in the structure of measurement, or in some seam of reality not yet given a name. On paper, the universe allows a mirror. Reverse the tick of the parameter called time, and the fundamental lines remain elegant. In Newton's mechanics, momenta simply change sign. The same orbits retrace themselves with clockwork grace. In the Lagrangian picture, the principle of stationary action is indifferent to whether a path is walked forward or back. Maxwell's equations, the clean grammar of light and charge, also survive a reversal when electric and magnetic fields transform with care. One field keeps its sign, the other flips, and the waves carry on. Quantum theory, with its complex amplitudes and fragile phases, hides a subtler symmetry, an anti-unitary operator, time reversal conjugates the wave function, repairs the spin, and leaves the Schrödinger equation unbroken. General relativity curves spacetime without preference for a direction, admitting solutions whose geometries do not single out an arrow. The bedrock of physics, viewed through formalism, appears ambidextrous. The world does not follow. Smoke disperses rather than reassembles. Ink enters water like prophecy, never like regret. A warm stone cools in shadow. The shadow does not feed the stone. Glass meets tile and becomes history. Radiation is emitted, not absorbed from empty skis in precisely coordinated waves. Telescopes survey galaxies whose stars are aging together, not rejuvenating in synchrony. Every macroscopic process carries the same asymmetry as a watermark. This is not an illusion of memory, it is a census of events. The equations consent to reversal, the phenomena refuse. The refusal sharpens around paradox. If the microscopic evolution preserves phase space volume, Liouville's theorem, then the fine-grained Gibbs entropy remains constant, yet the coarse-grained entropy measured by instruments and lived by organisms increases. If molecular dynamics is reversible, then, as Loschmidt pointed out, a magic flip of all velocities would send a gas back from equilibrium into order, collision by collision, a choreography of unmixing that seems both allowed and forbidden. Poincaré's recurrence theorem adds another blade. In bounded Hamiltonian systems with finite energy, trajectories wander near their starting points, eventually, almost surely. Zermelo raised this recurrence against irreversibility like a legal precedent. The shock is not that these results exist. The shock is that they coexist with a world that shows no taste for miracles of coordination. Electromagnetism provides another angle, bright and uneasy. Maxwell's equations allow two families of solutions for radiation, retarded waves that spread outward from charges and currents after they act, and advanced waves that converge on them from what is labeled the future. In calculations, both are legitimate. In skis, only one appears. Sommerfeld's radiative condition and the boundary assumptions of practical physics simply exclude advanced contributions. Antennas are treated as sources, not sinks. The asymmetry, once more, is not imposed by the differential equations, but by the conditions at infinity, the emptiness of the far field, the lack of a cosmic conspiracy to arrange incoming light. Wheeler and Feynman would later flirt with an absorber theory that banished advanced fields by demanding a perfectly absorbing universe. The ambition failed to reorganize electrodynamics, but the instinct remains. Boundary conditions do the quiet, decisive work. Quantum theory itself splits the light differently. The unitary evolution encoded in the Schrödinger equation is reversible and conserves the von Neumann entropy of an isolated state. Yet observations appear to induce a non-unitary projection, a collapse that chooses an outcome and burns the alternatives like dry leaves. Von Neumann's formalism writes the step as postulate. Experiments write it as habit. Decoherence softens the shock without erasing it, showing how environmental entanglement drives superpositions into effectively classical mixtures when their phases leak into innumerable, untracked degrees of freedom. The resulting Pointer states endure, while the cross-terms that would generate interference are attenuated beyond resurrection by any realistic apparatus. The symmetry of the fundamental equation survives. The practice of reality nurses an arrow through the irretrievability of information. The mathematics admits reversal. The world denies the accountant access to every ledger. Then comes a deeper discomfort. In one narrow corner of the standard model, time reversal is not a symmetry at all. In 1964, an experiment with neutral kaons uncovered CP violation, an asymmetry between matter and antimatter under the combined operations of charge conjugation and parity. The CPT theorem, a pillar of relativistic quantum field theory, insists that if CP is violated and CPT is preserved, then T is violated as well. Later measurements in B mesons confirmed and detailed this breaking, and the CKM matrix found its phase. Time, in this microscopic sense, does possess a dynamical bias, yet the bias is feeble. It whispers in rare decays, not in kettles or clouds. It may be essential to the cosmic preference for matter over antimatter. Baryogenesis demands CP violation and physics out of equilibrium, but it does not explain why cream refuses to jump from coffee back into its pitcher. The everyday arrow remains vastly larger than the amplitude of weak interaction T violation. The shock here bifurcates. The foundations allow symmetry, and where they do not, the asymmetry is too small to carry the macroscopic world. Gravity escalates the unease. Black holes born from collapse possess horizons that slice spacetime into regions that cannot exchange information. In the early 1970s, Bekenstein argued that a black hole's area is a measure of its entropy. Hawking's area theorem, proved within classical general relativity, showed that, barring exotic violations of energy conditions, the total horizon area cannot decrease. The second law seemed to find an ally in geometry. Then Hawking quantized the field around a horizon and found radiation with a thermal spectrum, a temperature proportional to surface gravity. Black holes evaporate slowly, like mountains sublimating into fog. If the process is truly thermal, information that fell in is not carried back out. The mapping from initial to final states is not unitary. A wall had been struck. Quantum mechanics preserves information. Hawking's calculation suggested a loss. The contradiction exposes the arrow at its most severe. Either the evaporation conceals correlations that preserve unitarity, and the appearance of thermality is only approximate, or the universe permits a fundamental irreversibility at the horizon. The Page curve, drawn from abstract considerations of entanglement, sketches how unitary evaporation would behave. Entropy of the radiation rises, peaks, and then falls as correlations return. For decades, neither a definitive calculation nor a decisive experiment resolved the conflict. The paradox became a compass pointing toward quantum gravity, and its needle quivers with the same question: what, at bottom, chooses direction? Cosmology, already implicated, becomes the stage where all arrows meet. The discovery of cosmic acceleration at the end of the 20th century, standard candles seen farther and dimmer than expected, implies horizons not only around black holes, but also around observers in a de Sitter-like universe. Horizons carry temperatures and entropies. They hide information and generate thermal baths. The large-scale fate of everything becomes tied to the presence of surfaces beyond which signals cannot return. If the cosmos accelerates forever, particles and galaxies drift past a boundary. Local physics relaxes into an equilibrium with a thin heat. The arrow is not merely the march from hot to cold. It is the growth and restructuring of horizons. The suggestion is unnerving. If the ultimate stage enforces forgetting, does the arrow survive even after gradients have flattened, written into the geometry of what can be known? Laboratories find echoes of reversal that only deepen the irony. Nuclear spin echoes, discovered by Hahn, demonstrate that a carefully engineered inversion of interactions can refocus dephased spins, conjuring a ghost of lost order from apparent equilibrium. Loschmidt echoes in cold atoms and quantum simulators. Similarly, reverse dynamics long enough to reveal how sensitivity to imperfections and environmental couplings explodes with scale. These experiments confirm both sides. The microscopic equations yield to reversal on demand, and the practical demands to maintain reversal grow so ferociously with size and time that the macroscopic world becomes a factory of entropy by mere existence. No fundamental edict forbids a teacup from unbreaking. The refusal is statistical, environmental, and unimaginably vast in its requirements. What remains after the shock settles is a pattern without a single author. The laws offer symmetries that extend a hand to both temporal directions. A small corner of particle physics withdraws the hand with a quiet, specific asymmetry that cannot carry the weight of oceans or stars. Electromagnetic radiation prefers retarded solutions, because the universe around sources is empty of conspiratorial, converging waves. Quantum measurement appears irreversible because environments are large, couplings are uncontrolled, and records are cheap to make but ruinously expensive to erase. Gravity writes one-way stories when horizons are present and may bind entropy to area with a devotion that unites geometry with thermodynamics. Everywhere the arrow is a composite. Boundary conditions, typicality, coarse graining, and inaccessible information weave a direction from ingredients that, separately, do not insist on one. The discomfort this leaves is existential as much as technical. If the arrow is not carved into the equations, it must be planted in the conditions, particularly the initial ones. A low-entropy beginning would explain how equilibrium could be so far away that stars still burn and minds still think. But why such a beginning? Inflation, the rapid early expansion that levels curvature and irons away irregularities, can magnify a smooth patch into a cosmos. Whether it explains the low entropy or assumes it through a special state of the inflaton remains disputed. Penrose's suggestion that the early universe possessed vanishing whale curvature, dramatically suppressing gravitational degrees of freedom, gestures at a rule deeper than dynamics, a geometric boundary law. Competing cosmologies propose mirror worlds, Janus points, or CPT-symmetric extensions beyond the hot Big Bang, each trying to restore symmetry globally while explaining asymmetry locally. The shock of irreversibility thus becomes a question about origin, not about motion. The asymmetry of time may be a letter written on the first page of the book rather than a rule in the grammar. In the meantime, the arrow governs. Engines age, species adapt and vanish, black holes merge and ring down with areas that do not shrink, laboratories coax qubits into temporary innocence before heat reaches them with its soft insistence. The symmetry of laws is genuine, the asymmetry of experience is relentless. Between them lies the terrain to be mapped, the scale at which coarse graining becomes destiny, the structures that create records faster than they can be unmade, the horizons that render information effectively lost, and the boundary conditions that set the stage. The scientific shock endures because it is honest. The universe speaks two dialects at once, one of reversible equations, one of irreversible histories, and the translation, though underway, is not yet complete. The closer the gaze, the less the arrow resembles a command and the more it looks like a census. At microscopic scales, motion preserves measure. Flows of points in phase space stretch and fold like dough without tearing. Liouville's theorem declares that the fine-grained volume occupied by an ensemble of microstates is constant under Hamiltonian evolution. If entropy were computed with an infinitely sharp partition, nothing would change. Yet instruments, brains, and stars do not track infinity. They draw grids that blur. Coarse graining, averaging over cells larger than the filigree made by dynamics, turns the silent choreography of stretching and folding into an apparent diffusion. What begins as a compact patch filaments across phase space until each coarse cell receives a hair of occupancy. Once the grid is set, the count of occupied cells grows. The number called entropy increases not because something is created, but because resolution is limited. The arrow enters with the decision to look with finite eyes. Statistics gives this decision its teeth. Most microstates compatible with a macroscopic description look typical, in the sense that they realize the large numbers predicted by equilibrium. Maxwellian velocity distributions, uniform mixing, the dull calm of stationarity. The rare microstates that generate reversed movies, creams unmixing, smoke refocusing, exist in profusion less than negligible when counted against the sky's arithmetic. Boltzmann's formula, engraved later on his stone, ties entropy to the logarithm of multiplicity. More ways to be disordered than to be arranged mean that evolution from arranged toward disordered is almost certain once coarse variables are chosen. Typicality, not compulsion, draws the line forward. Still, typicality by itself is not origin. A roll downhill requires a height to descend from. The past hypothesis answers in the language of boundary condition. The universe began in an extraordinarily low-entropy macrostate, a special configuration against which typical evolutions would be born asymmetric. Within that hypothesis, the second law is not a law but a theorem of vast probability. Given a special start, almost every allowed microstate consistent with it will evolve so that coarse-grained entropy increases toward what is labeled the future. The hypothesis does not compute the specialness. It presumes it, audacious and plain. Every boiling kettle and dissolving cloud, every aging star and growing coral follows from that presumption like a footnote. Gravity reshapes what special means. For a gas in a box, uniformity is the generic macrostate because it maximizes ways to distribute particles evenly. For a self-gravitating fluid, uniformity is fragile, perched on a summit. Clumping first ripples, then filaments and halos, then stars and black holes, explores far more of the phase space. Gravitational entropy, though hard to define in general spacetimes, takes on clarity in extreme cases. Black holes carry an entropy proportional to their horizon areas. Mergers obey an area increase theorem that mirrors the second law. From this vantage, a nearly smooth early universe, the one mapped by the microwave background with temperature variations of only parts in 100,000, looks astonishingly low in gravitational entropy. Roger Penrose framed the contrast geometrically. The early cosmos appears to have had negligible Weyl curvature, the free, tidal part of spacetime curvature that encodes gravitational degrees of freedom. As structures form, the Weyl tensor awakens. As horizons grow, the entropy ledger swells. The arrow in this reading is gravity's appetite for irregularity. Cosmic inflation complicates and clarifies. A brief epoch of accelerated expansion can take a small, smooth patch and iron it into a cosmos of extraordinary flatness and uniformity, while quantum fluctuations stretched by the expansion seed the structures later seen in galaxies and clusters. Inflation explains the broad, simple canvas on which complexity later paints, but whether it explains the initial low entropy or assumes it remains contested. To inflate, a scalar field must occupy a high, nearly constant potential and be sufficiently homogeneous across a region large enough to start the process. These conditions may themselves be rare. If inflation is eternal in some directions of field space, it plants a multiverse of pocket universes separated by inflating horizons. Measure problems then arise when one asks what is typical across such an ensemble. The question boomerangs. Does inflation lower entropy by diluting inhomogeneities, or does it begin from a rare, tuned state whose low-entropy character is merely exported to a larger domain? The past hypothesis may shift location, from the hot, dense plasma to the onset of inflation, but it does not vanish. Between microscopic reversibility and cosmic boundary lies the daily miracle of facts. Quantum mechanics describes isolated systems by wave functions or density matrices that evolve unitarily and reversibly. Yet macroscopic definiteness emerges with relentless ease. Decoherence traces the path. A system coupled to its environment becomes entangled with innumerable degrees of freedom. Relative phases between components of a superposition disperse into correlations with those unobserved variables. The reduced state of the system, obtained by tracing over the environment, becomes diagonally dominant in a preferred basis, the pointer states, selected by the nature of the coupling. Schrödinger's equation was never violated. Nonetheless, interference between macroscopically distinct alternatives becomes unobservable for any realistic agent. The arrow here is practical and ferocious. Recohering the phases would require gathering, revering, and phase-aligning environmental degrees of freedom, as numerous as specks of light in a sunbeam. As decoherence suppresses interference, a second phenomenon rises: redundancy. Records of macroscopic outcomes are not stored once but proliferated. Photons scatter off a dust grain in configurations that encode its position. Molecules in air carry imprints of events. Surfaces and sensors and synapses layer copies upon copies. Some call this sprawl of agreement quantum Darwinism. States that leave many imprints are the ones robustly accessible to multiple observers. In such a world, the past is the set of states redundantly recorded. The future is the set not yet written down. The psychological arrow aligns with the thermodynamic because making and storing records consumes free energy, increases entropy, and spreads correlation, an irreversible expenditure of order in exchange for knowledge. Information thermodynamics welds the intuitive link into a bound. Landor's principle states that erasing one bit of information in a system at temperature dissipates at least of heat. Maxwell's demon, that imagined accountant who sorts fast and slow molecules to decrease entropy, must pay an energetic price to store, process, or erase the information used in sorting. The full, honest ledger obeys the second law. In living matter, the same accounting governs. Replication, metabolism, neural computation, the whole edifice of sensation and memory, operates by consuming gradients and discarding heat. What is called remembering is a thermodynamic transaction. What is called forgetting is a different one. The mind's one-way sense of becoming is not a ghost layered atop physics, but a trace carved by physics through tissues, silicon, or ink. Radiation's directionality threads through these considerations as boundary writ large. Maxwell's equations are symmetric. Retarded waves as solutions are preferred by assuming no incoming interference from infinity. In a universe with a low-entropy past, sources act into emptiness rather than into a prearranged chorus of canceling waves. The electromagnetic field, in practice, is an arrowed messenger because the environment does not conspire to send advanced messages. The same is true of diffusion, chemical reactions, fracture, and flow. The future lacks the precise conspiracies that the past is known to have lacked. The alignment of arrows, thermodynamic, electromagnetic, cosmological, psychological, emerges, then, as a consequence of a single asymmetry in initial conditions rather than many unrelated diktats. Even the supposed constancy of entropy admits subtleties when quantum information is weighed. Fine-grained von Neumann entropy of a closed system remains fixed under unitary evolution. Coarse-grained entropies, defined by ignoring inaccessible correlations, grow as entanglement spreads. Black hole thermodynamics magnifies the distinction until it reshapes theory. If black holes evaporate thermally, then the radiation's entropy rises monotonically as the hole shrinks, clashing with unitarity. If evaporation is unitary, the entropy of the radiation must trace the page curve, up, then down, as correlations encoded behind the horizon seep out. Recent progress in gravitational path integrals and quantum extremal surfaces suggests a route toward the unitary answer by associating islands inside the horizon with the entanglement wedge of the radiation. In that picture, the arrow becomes a tale of where information is counted and who is allowed to see it. Laboratories translate these abstractions into timed experiments. Cold atom arrays show how isolated quantum systems approach equilibrium through eigenstate thermalization, with observables relaxing despite hidden coherence in full many-body states. Many-body localization, at odds with thermalization, traps systems away from equilibrium, creating islands where the arrow's usual rush slows to a crawl. Loschmidt echoes and spin echoes demonstrate engineered reversal that collapses under the smallest tilt toward imperfection or coupling to unmonitored degrees of freedom. The lesson is consistent. The arrow is not invulnerable in principle. It is invincible in practice once scale and openness cross modest thresholds. On planetary surfaces, the narrative adopts biogeochemical grammar without changing its theme. Sunlight arrives as a stream of low-entropy photons and leaves as a warmer spray of high-entropy ones. Life writes complexity by spending the difference. Snowflakes form symmetry by dumping heat. Crystals grow by losing freedom to the environment. Cities pulse by burning gradients stored over geological ages. Every ritual of order is a transaction with disorder. No edict forbids the local rise of intricacy. The price is paid to the universe that carries the heat away. What remains, after the deeper investigation, is not an explanation that abolishes the arrow, but a web that sustains it. Coarse graining turns Hamiltonian invariance into practical increases. Typicality ensures that increases are overwhelming. The past hypothesis anchors direction in a special beginning. Gravity inverts uniformity into improbability and draws entropy upward through structure and horizon. Decoherence and redundancy knead probabilities into facts. Information processing binds memory to heat. Boundary conditions purge advanced fields from the sky. No single strand holds the weight alone. Together they draw the bow that looses the flight called time's arrow. Yet the bow's wood is still mysterious. Why should the early universe have been so smooth that galaxies, stars, and minds could emerge only by moving away from that smoothness? Does inflation answer by dynamical law or by relocating the miracle? Could whale curvature have been constrained to vanish at the birth of spacetime by a principle not yet seen? If a mirror cosmos exists across a hidden seam, do two arrows depart from one neck like swans in opposite directions? These are not rhetorical ornaments but working questions. The deeper the account, the more spare the confession. Dynamics alone do not choose the sign. Initial conditions do, and their specialness is the last fact for which physics still lacks a cause. So the investigation returns to the sky, where evidence lives in maps of ancient light and in the distribution of galaxies across time. It returns to laboratories, where qubits whisper about reversibility while heat reminds them of the world. It returns to equations, whose symmetries do not lie, and to horizons, whose silences do not either. The arrow remains a composite object, statistical, gravitational, informational, carved from a single asymmetry at the beginning and kept sharp by a universe that favors records over erasures. In such a place, becoming is not a contradiction of being. It is the method by which being is remembered. The puzzle grows sharper when horizons enter the frame. At the close of the 20th century, standard candles, type Ia supernovae in remote galaxies, arrived dimmer than a decelerating universe would allow. The distances were longer, the ages older. Together with the smoothness of the cosmic microwave background and the clustering of galaxies, the measurements marked a turn. Cosmic expansion is accelerating. A cosmos ruled at late times by vacuum-like energy does not merely expand. It shelters each observer behind a horizon of limited reach. Beyond a certain distance, recession outruns any signal. The universe gains a boundary not of matter but of knowability. Such horizons carry thermodynamic accents. In de Sitter spacetime, they possess a temperature and an entropy, a faint thermal bath at a temperature proportional to the Hubble scale, and an entropy proportional to the horizon's area in Planck units. The geometry itself inherits a ledger. If black holes suggested that gravity counts microstates along surfaces, de Sitter space announces that the largest, emptiest spaces count as well. The arrow gains a new register. It is not only the migration from gradients to equilibrium, it is the deepening of ignorance enforced by expanding boundaries. An accelerating universe becomes a grand version of a laboratory sealed off from its heat reservoir, a system that must accept a modest, unarguable warmth from a wall that recedes forever. Extrapolated far into time, the acceleration provokes a paradox of typicality. A universe that lasts indefinitely with nearly constant vacuum energy approaches a quiet state in which rare thermal fluctuations are the only artists at work. Given enough eons, those fluctuations can rise to absurdity. A brain assembled by chance from thermal noise, complete with false memories and a momentary sense of coherent surroundings. If the future is long enough, such Boltzmann brains become statistically common compared to observers assembled by stellar evolution and chemistry. A credible cosmology must forbid that inversion of meaning, or at least make it measure zero. The arrow here becomes a constraint on theory. Whatever explains direction must also rule out a world where typical minds are phantoms of heat. The requirement presses back on inflation, on horizon thermodynamics, on measures in a multiverse, tightening the weave of ideas with an ethical edge disguised as statistics. Black holes then return, not as graves but as classrooms that stage the most argued experiment imagination can supply. The information paradox, once a clash of principles, has been recast with the precision of an entanglement audit. The Page curve, anticipating how the von Neumann entropy of Hawking radiation should grow, and then fall if evaporation is unitary, turns from conjecture into a calculation in certain gravitational models. By allowing spacetimes to contribute saddles with new geometric features, quantum extremal surfaces, and the islands they bound inside horizons, gravitational path integrals can reproduce Page curve behavior. Information seems to leak out after all, not by abandoning thermality entirely, but by reassigning what counts as the system for measuring entropy. The ledger is kept whole by enlarging the region treated as part of the radiation's entanglement wedge. The arrow in this picture does not dissolve, it relocates. Entropy still rises for coarse, local observers with limited access. Only when an observer can include the island in the bookkeeping does the late time fall occur. Reversibility is preserved in a global, carefully chosen sense, while irreversibility endures for creatures bounded by practical horizons. The escalation here is conceptual. The arrow depends on who is allowed to count, and gravity decides membership. Cosmology extends the lesson into its beginning. Inflationary scenarios, with their rapid expansion and stretched quantum fluctuations, predict an almost scale-invariant spectrum of primordial ripples. The microwave background agrees, but inflation's global structure may be unruly. In many models, quantum fluctuations of the inflatoned field perpetuate inflation in some regions while ending it in others, birthing pocket universes without end. If so, the observable cosmos is one sample among uncounted cousins, each with its own local arrow inherited from initial conditions inside that pocket. A measure must be chosen to say which pockets matter, and measures are treacherous. They can overcount late-time volumes or undercount early-time seeds. They can grant perverse importance to rare events if the bookkeeping is ill-posed. The arrow's status becomes entangled with a census taken on scales that no instrument will ever survey. The mystery deepens by escaping both microscope and telescope, settling briefly in the grammar of probability. Other proposals answer with symmetry rather than abundance. Some suggest that the Big Bang is not a singular origin but a neck, a minimal entropy surface from which entropy rises in two temporal directions. On one side lies the history known to maps and fossils. On the other, a mirror history with its own arrow pointing away from the shared waste. In that Janus cosmology, time's direction is local and bilateral. Globally, the universe honors a deeper time reversal symmetry. The elegance is severe. No past hypothesis is needed beyond the existence of the neck. Typicality does the rest twice. Yet such pictures must reconcile with the observed arrow's early alignment, nucleosynthesis, recombination, structure formation, stellar burning. Every rung on the cosmic ladder ascends the same way. The second arrow cannot leak into this one, nor can signals cross the neck to spoil locality. The symmetry saves a principle while quarantining worlds. The escalation is a test of coherence. Symmetry alone is not a shield against contradiction. Closer to hand, reversals can be made and broken in the same breath. Nuclear spin echoes revive order by flipping interactions midway through evolution. In almost isolated quantum simulators, Loschmidt echoes rewind many-body dynamics for a few dozen microscopic ticks. But imperfections, minuscule couplings to an environment, tiny control errors, grow exponentially in their capacity to spoil the rescue. Scrambling, the rapid delocalization of quantum information across degrees of freedom, accelerates the failure. In chaotic systems, the butterfly effect is not a metaphor but a metric. Practical irreversibility is not a shrug. It is a theorem of sensitivity. The arrow is a blade honed by chaos, nicked only where isolation is engineered and briefly maintained. Radiation sharpens the edge with boundary conditions that harden into cosmology. Retarded electromagnetic waves, those that flow outward from sources, are selected by assuming emptiness in the far field and the absence of conspiracy among distant charges. But emptiness is not a metaphysical default. It is an empirical summary of a low-entropy past. A cosmos with a smooth beginning contains no bath of advanced radiation arranged to meet future charges at the right instance with the right phases. What looks like a choice of solution becomes an inference about history. The arrow of radiation, the arrow of thermodynamics, and the arrow of memory follow from the same absence. The past lacked the precise correlations that would be required to paint the future backward. The mystery deepens because the same sentence explains so much and yet leaves untouched the reason the past had that character. Information, once a metaphor, tightens into a currency with denominated bills and audited transactions. Landor's bound links erasure to heat, fluctuation theorems, Jarzynski's equality and Crookes' theorem, quantify how entropy behaves in small systems far from equilibrium, where the arrow still exists but is textured by rare, measurable violations on short timescales. These theorems do not undermine direction. They underwrite it by turning exceptions into rules about probabilities. Even the deviations pay interest to the second law when averaged over many runs. The arrow's grip is statistical and exact in that precise sense. Chance is allowed, but accounts must balance. Holographic dualities pull the thread toward an unexpected loom. In certain strongly coupled quantum systems, a gravity theory in a higher dimensional spacetime encodes their dynamics. In this correspondence, the growth of entanglement in the boundary theory maps to the growth of extremal surfaces in the bulk. Thermalization on the boundary resembles black hole formation in the bulk. Decays of order look like horizon settling. An arrow in one language becomes an arrow in the other. Geometry and information evolve in lockstep, suggesting that irreversibility may be a property of spacetime itself when seen through the right lens. The mystery escalates by seeming to unify things earlier kept distinct: heat and area, memory and surface, time's direction and the architecture of the world. Acceleration's future carries one more tension. If vacuum energy remains constant, galaxies outside a shrinking sphere of influence will flow beyond contact. Night will empty. Local groups of bound galaxies will collapse into black holes, which will evaporate over fantastically long spans, drizzling radiation into a thin bath that settles toward equilibrium. In such a world, the sources of low-entropy photons that power biology, weather, and thought will fail one by one. The arrow will persist as a tendency in small systems that can still exchange heat, but its grand stage will narrow. If the de Sitter temperature sets a floor, fluctuations will never cease entirely, but their products will be rare and brief. The very concept of history begins to blur when witnesses vanish and records decay. The arrow, once a global narrative, becomes a local habit in pockets of matter that refuse oblivion as long as physics allows. None of this erases the central surprise. The laws invite reversals. The universe does not RSVP. Where asymmetries exist in dynamics, such as in weak interaction T violation, they are too slight to erect the macroscopic slope. Where horizons exist, they carve one-way provinces without writing a prohibition into equations, merely into access. Where quantum mechanics reigns, unitary evolution respects a timeless balance even as decoherence and redundancy write indelible pages for beings with limited reach. Each layer, cosmic, gravitational, quantum, informational, adds weight to the same direction while passing the question upward. What fixed the beginning so that all these currents could align? So the escalation is not an alarm but a narrowing. The territory where the arrow could hide as a feature of dynamics has been surveyed and found insufficient. The territory where it can arise from boundary conditions and typicality has been mapped from boilers to black holes, from laboratory echoes to cosmic horizons. What deepens is not ignorance but the contour of the remaining ignorance. It now lies in the origin of the conditions that made an arrow possible at all, in the measures that keep typicality meaningful in vast, inflationary ensembles, in the accounting of information across surfaces that split spacetime into seen and unseen, in the requirement that theories not flood eternity with counterfeit minds. The scene at this juncture is quiet. The microwave background still hums at 2.7 Kelvin, with tiny Gaussian ripples that match inflation's song. Supernova light curves continue to write acceleration on graphs of redshift and distance. Gravitational waves pass like whispers from black hole mergers whose combined horizons grow as the second law of geometry demands. Quantum simulators test reversals and lose the race against imperfection in predictable ways. And telescopes watch more galaxies drift toward the edge of influence where no message can return. The mystery does not shout. It endures in the way all these facts share a bias, as if listening to a wind that has always blown from the same direction. The deeper the gaze, the clearer the wind's origin must be, and the more distant it remains, somewhere beyond the first page of time. The arrow's prominence invites explanations that are not commands but architectures. Some begin at the first page and write special in delicate ink. Others adjust the alphabet of geometry. A few ask whether time itself is not a primitive but a consequence of relations that ripen into direction. Each proposal trades austerity for reach, trying to bind steam, stars, and memory to a single source. One family keeps dynamics untouched and places the burden on the boundary. The past hypothesis states, with plain courage, that the universe began in an extraordinarily low-entropy macrostate. From that simple line, typicality does the rest. Almost every microstate compatible with such a beginning evolves so that coarse-grained entropy increases away from it. The power of the claim is its silence. It does not explain why the initial macrostate was so rare. It makes rarity the starting point rather than the product. Engines, galaxies, and biographies then fall outward from a special dawn through a universe where records are easy to make and hard to erase. The arrow is not a law. It is a boundary condition that selects a direction for almost every possible history. Gravity complicates and refines this stance. Roger Penrose has argued that the early universe's remarkable smoothness is not simply a thermal feature, but a geometric one. The Weyl curvature, the free, tidal part of spacetime curvature, appears to have been essentially absent at the Big Bang. His Weyl curvature hypothesis would enforce a vanishing of gravitational degrees of freedom at the origin, rendering the early cosmos astonishingly low in gravitational entropy. As structures form, the Weyl tensor awakens. With horizons, gravitational entropy swells. In this reading, the arrow emerges because the universe begins in a state where gravity has not yet opened its vast book of microstates. The proposal is not a complete theory. It gestures at a rule that geometry might obey at birth, a constraint deeper than known dynamics, and it aligns the thermodynamic with the gravitational without invoking new particles or forces. Inflation offers a dynamical instrument that can stretch small smoothness into cosmic grace. A scalar field lingering on a plateau of potential energy drives an exponential expansion. Curvature and irregularities are ironed flat. Quantum fluctuations, stretched to astrophysical scales, seed the tiny anisotropies later seen in the microwave sky and the scaffolding of galaxies. Inflation explains several puzzles at once: flatness, horizon, monopoles, and it predicts statistical patterns that observations have affirmed. Yet the arrow's accounting remains contested within that success. To begin inflating, the field must be coherent and high on its potential across a region large enough for the process to take hold. Such a region is atypical in many measures of initial states. If inflation is eternal in some directions of field space, it generates a multiverse of pocket universes where arrows may sprout locally from shared rules, but typicality becomes a delicate assembly of choices about measure. In this view, inflation magnifies order but may not mint it. It exports the past hypothesis into the conditions needed to start the inflating phase, and replaces a single miracle with a debate about probability across unreachable domains. Another route preserves global symmetry by doubling the story. In CPT-symmetric and Janus-style cosmologies, the Big Bang is reimagined not as an absolute beginning but as a neck, a minimal entropy surface, through which two temporal directions flow. On one side lies the familiar expansion, nucleosynthesis, recombination, and the slow rise of structure. On the other, a mirror cosmos evolves with its arrow pointing the other way. The global picture honors time-reversal symmetry. Locally, arrows are as strong and aligned as they appear here. Such scenarios can weave in otherwise puzzling facts: why neutrinos are so light, why certain symmetries are intact, by tying them to boundary conditions at the neck. Their challenge is empirical modesty. The opposite side is causally disconnected, and the principle that defines the neck must be precise enough to avoid ambiguity while accommodating observed initial smoothness and statistics. Symmetry, though elegant, must share a room with constraint. At smaller scales, the question turns on the architecture of quantum facts. Decoherence shows how environmental entanglement selects stable pointer states, suppresses interference, and proliferates records. The many worlds interpretation leans into this unitary story. There is no fundamental collapse. Branches of the wave function evolve into mutually decohered histories that do not recollect one another. The arrow, then, is the growth of entanglement and the branching of records. Each branch inherits the past hypothesis and experiences entropy increase in its own coarse-grained ledger. In this frame, nothing stochastic is added to the dynamics. Probabilities arrive as weights on branches that feel classical because redundancy has made them so. The cost is metaphysical breadth, a plenitude of outcomes wandering in a high-dimensional amplitude space, each with the same thermodynamic slope. Objective collapse models, GRW and CSL among them, propose a more radical move. They supplement Schrödinger's equation with spontaneous, stochastic collapses that localize wave functions in space. The collapses are rare for microscopic systems and frequent for macroscopic superpositions, building irreversibility into the fundamental rules. The arrow becomes dynamical, not merely statistical. These models make testable predictions: tiny deviations from quantum unitary evolution, faint heating, or altered interference, and experiments continue to push the allowed parameter range. If evidence were found for such collapses, time's direction would become part of the syntax of microphysics. In their absence, the attraction of parsimony keeps the unitary camp strong. Beyond dynamics and interpretation lies a suspicion that time itself is not elemental. Canonical quantum gravity, when cast into the Wheeler-DeWitt equation, yields a stationary object. No explicit time parameter appears. In such a frozen formalism, change must be relational. Clocks are subsystems entangled with others. The Page-Wooter's mechanism shows, in toy models and with laboratory analogs, how conditional states can generate an effective flow. When a system is conditioned on a clock's readings, correlations produce a sequence that functions as evolution. Carlo Rovelli's thermal time hypothesis takes a different tack. Given a state and the algebra of observables, there exists a canonical flow, the modular flow, that can play the role of time. The arrow is then tied to the state's statistical asymmetry rather than a background parameter. These approaches do not yet deliver a unique empirical explanation of the cosmic arrow, but they tilt the axis. Direction becomes the shape of correlations, not the shadow of an external variable. Information-theoretic frameworks add a further layer. In quantum statistical mechanics, the KMS condition characterizes equilibrium in algebraic terms, encoding a direction in correlation functions. Fluctuation theorems, Jarzynski, Crookes, quantify the probabilities of observing entropy-decreasing trajectories in small systems driven far from equilibrium, showing that such events are not forbidden but exponentially suppressed in proportion to the entropy produced. These are not ad hoc patches. They are exact relations. The arrow here is the skew in those probabilities, a tilt that vanishes in microscopic limits and dominates in macroscopic practice. Complexity, in some holographic proposals, grows even when entanglement saturates. If the volume or action of a wormhole in a dual spacetime tracks computational complexity, then a second arrow persists in the growth of minimal resources needed to reconstruct states. It is speculative, ambitious, and points toward a world where geometry and computation share a ledger. Holography ties these strands into a tapestry. In certain conformal field theories, the entanglement entropy of a region is proportional to the area of an extremal surface in a higher dimensional gravity theory. The Ryu-Takayanagi prescription, refined by quantum extremal surfaces that include bulk entanglement contributions. Thermalization on the boundary resembles black hole formation in the bulk. The Page curve for evaporating black holes can be reproduced by allowing new saddles, islands, in gravitational path integrals. In this dictionary, unitarity is kept whole, and the apparent thermality of Hawking radiation is recognized as an artifact of limited access, corrected at late times by subtle correlations. The arrow, then, is observer relative. For agents who cannot include the island in their bookkeeping, entropy rises and information is lost for all practical purposes. For a hypothetical, globally counting auditor, reversibility is restored. Geometry does not erase direction. It distributes it across horizons and wedges. Cosmic requirements push back on speculation with the firmness of numbers. Any explanation must prevent a future dominated by Boltzmann brains, observers springing from rare thermal fluctuations with counterfeit memories, lest typicality collapse into farce. It must accommodate baryogenesis or leptogenesis, microscopic CP violation and departures from equilibrium that allowed matter to survive its annihilations with antimatter. It must account for the alignment of arrows, the fact that thermodynamic, radiative, and psychological directions point the same way. It must respect what telescopes see, nearly scale-invariant primordial fluctuations, acoustic peaks in the CMB, an expansion history that accelerates at late times, and large-scale structures whose statistics match cold, dark matter under gravity's rule. Theories that satisfy these constraints earn the right to be called candidates rather than stories. Where this leaves the mystery is instructive. If the past hypothesis is correct in spirit, then the arrow is not a theorem of dynamics but a feature of the cosmos, boundary data. If a geometric constraint like vanishing whale curvature enforced that boundary, then gravity itself, through the architecture of curvature, would be the author of direction. If inflation is essential, then the arrow rides on fields that flatten and fluctuate in ways that are simple in one description and fine-tuned in another. If time is emergent, then direction is the character of correlations that deepen and spread, while clocks are merely indexes woven from entanglement. If holography is the correct grammar, then the growth of entanglement wedges and the evolution of extremal surfaces encode in geometry the statistics that brains translate as before and after. The cost of each answer is clear. Boundary conditions demand an explanation they do not supply. Geometric hypotheses require principles not yet derived from deeper laws. Inflation courts measure problems and does not wholly banish specialness. Emergent time programs must extract unique, testable arrows from relational flows. Holography flourishes in spacetimes unlike the accelerating universe observed, and its extrapolation beyond those arenas is a guiding hope rather than a proven bridge. Objective collapse seeks signatures that have not yet appeared. Many worlds asks for comfort with plenitude and derives probabilities from structure. None is a closed room. All are open windows that admit the same wind. Through these windows, one fact remains constant. The arrow is a pattern that ties statistics to history, boundary to becoming, and information to geometry. It is the habit of a universe that began in astonishing simplicity and has not yet tired of making records. Any satisfactory theory will speak softly where the world speaks loudly. In maps of ancient light, in the ringdown of black holes, in the failure of advanced radiation to arrive, in the ease with which memories accumulate and refuse erasure. The speculation that survives will be the one that lets these ordinary miracles proceed without stage tricks. one that shows how a cosmos bereft of conspiracies can still prefer a direction without ever writing the preference into its most symmetric laws. The arrow is not studied with a single instrument. It is triangulated by many. Sky and laboratory, cryostat and desert plateau, collider ring and mountaintop mirror. Each device tests a different clause in the story, and the clauses must agree. The question is old. The measurements are young. They proceed with a calm insistence that suits the subject. Time's one-way habit, examined in the places where reality keeps its best records. First, the cartography of beginnings. The cosmic microwave background, an afterglow chilled to 2.725 Kelvin, still holds the earliest legible script. Kobe discovered its near-perfect blackbody spectrum. WMAP and Planck etched its anisotropies with high precision, revealing tiny temperature ripples and polarization patterns that trace the seeds of structure. Experiments now turn toward the faintest curls in that polarization, the B-modes that would whisper of inflationary gravity waves. On the high plateaus of Atacama and the South Pole, receivers stare into dry, cold air. Arrays plan to delens the sky, removing the confusions added by intervening structure so that a primordial signal, if present, can be heard. The Simons Observatory, then CMB-S4, promises sensitivity deep enough to chase tensor-to-scalar ratios that once seemed unreachable. Even a null result is a verdict. Each upper bound trims the space of initial conditions that could have drawn the first arrow. Beyond the afterglow, the late universe supplies a second ledger in the distribution of galaxies and their distortions of light. Redshift surveys measure how structure grows. Baryon acoustic oscillations provide a standard ruler in the pattern of clustering. Instruments chart the web, from ripples blown up by inflation to filaments drawn by gravity's patient hand. Weak gravitational lensing, the slight shearing of background galaxies by foreground mass, adds a complementary measure of both geometry and growth. A trio of new eyes, Euclid from space, the Rubin Observatory scanning the southern sky, and the Nancy Grace Roman Space Telescope in the coming years, compose an orchestra: spectroscopy for precise distances, deep imaging for shapes and transients, time domain maps for supernovae that renew the classical standard candle. Together, these surveys test whether acceleration is an unchanging vacuum energy or something subtler, whether gravity itself bends on cosmological scales, and whether the growth of clumps agrees with the expansion history. The arrow's cosmological half, its tie to horizons, and to the deepening of ignorance enforced by recession, sits inside these error bars. Black holes convert speculation into silhouette. The Event Horizon Telescope stitched millimeter-wave dishes across Earth into a planet-sized lens, imaging the photon ring of M87 and the glow around the Milky Way's central object. Variability, polarization, and closure phases act as thermometers and barometers for plasma skimming the point of no return. Proposed upgrades: the next generation EHT with more baselines, shorter wavelengths, and faster cadence, aim not only for higher resolution but for movies, ringed on waves of light that could betray deviations from Kerr geometry. In parallel, ground-based gravitational wave observatories harvest the coalescence of compact objects. Each chirp carries horizon physics in its amplitude and phase. Each ringed-on tests the no-hair theorems. Each area increase across a merger echoes a geometric second law. Future detectors: the Einstein Telescope and Cosmic Explorer on Earth, and LISA in space, extend the portrait to lower frequencies where supermassive binaries write long operas. The area theorem, the page curve, the mapping from information to geometry, these ideas gain or lose credibility on the strength of spectra and time series. Symmetry tests probe a different scene. LHCb, Bell II, and other flavor experiments refine the parameters describing CP violation in quark transitions, weak asymmetries that, through the CPT theorem, imply time reversal violation. Neutrino experiments, long baseline beams crossing crust and mantle, and the deeper water or ice volumes waiting for their oscillations seek the leptonic CP phase that would hint at matter, antimatter preferences beyond the quark sector. Electric dipole moment searches exploit exquisite control of spins and fields to hunt for tiny T-violating signatures. Null results constrain models of baryogenesis. None of these effects approaches the magnitude of everyday irreversibility. Nonetheless, their existence matters. They demonstrate that time symmetries are not immaculate, and that the early universe possessed the ingredients for matter to survive annihilation. The arrow is not delivered by these asymmetries, but their presence keeps the world's grammar honest. Antimatter feels gravity. This simple sentence took decades to write experimentally. Trapped antihydrogen, cooled and released, falls in Earth's field with acceleration consistent with ordinary matter, within current uncertainties. It is a quiet confirmation of general relativity's indifference to charge, a test of CPT symmetry, and a rebuke to exotic hopes that antimatter might rise. In the context of the arrow, such results close doors that would have led to dynamical asymmetries large enough to bear the macroscopic world. The remaining doors are boundary conditions, statistics, and geometry. Closer to the scale of memory and heat, laboratories study irreversibility one bit at a time. Single electron boxes and colloidal particles in optical traps have verified Landor's bound. Erasing information costs at least of dissipated heat. Demons built from feedback controllers sort particles and pay the bill when their memory is reset. Fluctuation theorems, Jarzynski's equality and Crookes' relation, are measured as distributions of work in tiny engines, where trajectories sometimes run entropy backward but always obey the exponential weight that makes the second law hold on average. The arrow at this scale is not absolute. It is statistical, and the statistics are now laboratory facts with uncertainties and error bars. Quantum simulators turn unitary time into something that can be rewound briefly and then lost again. Trapped-ion chains implement spin models with tunable interactions. Rydberg atom arrays draw lattices of entanglement. Superconducting qubits simulate many-body dynamics with exquisite, but not perfect, control. In such systems, out-of-time order correlators quantify scrambling, the delocalization of information that makes retrieval exponentially difficult. Loschmidt echoes reverse time for a moment and reveal the sensitivity that kills reversal at larger scales. Many-body localization, by contrast, arrests thermalization, preserving local memory in the midst of interactions. These results sketch the arrow's phase diagram. Isolation and disorder can slow or redirect it. Openness and chaos sharpen it. Precision timekeeping measures the slope of the arrow against gravity's gradient. Optical lattice clocks, stable to parts in 1018 and beyond, resolve gravitational redshift across centimeter and even millimeter height differences. Networks of clocks linked by fiber and free space optics form the first meshes of chronometric geodesy, maps of gravitational potential drawn not with falling masses or satellite tracks, but with the frequency of light. In general relativity, time dilates in deeper wells. Such measurements turn the equivalence principle into daily calibration. The arrow's flow is not universal in rate. It is braided through geometry, and clocks now read the braid directly. The sky adds another choir at nanohertz frequencies. Pulsar timing arrays, the metronomes of millisecond pulsars watched by radio telescopes across continents, have heard a stochastic gravitational wave background in the timing residuals. The signal likely arises from supermassive black hole binaries, each pair a punctuation mark in the history of galaxy growth. Over years to decades, the correlated shifts in pulse arrival times trace a long, low hum. If confirmed and mapped, this background will chart the distant assembly of structure, test whether cosmic strings or other exotic relics contribute, and refine how horizons grow in the slow motion of the largest scales. The arrow appears here as an accumulation of mergers, an irreversible knitting of galaxies into larger narratives. Observatories that trade spatial resolution for area find the thermodynamic slope in gas and dust. X-ray telescopes image cluster atmospheres, measuring entropy profiles set by shocks and feedback from active galactic nuclei. Submillimeter surveys map cold dust where stars form, counting how gravity's clumping spends potential energy to ignite fusion. Spectroscopic campaigns measure metallicity as a fossil record of past thermonuclear processing and dispersal. Even planetary systems carry the signature. Disks dissipate, migration damps, and late heavy bombardments sculpt surfaces that will not unscrape themselves. In each case, the arrow is a ledger written in temperatures and lines, in chemical ratios and shock edges. Holographic ideas, however abstract, also submit to tests at the edges of feasibility. If complexity in a quantum system maps to a geometric volume or action in a dual spacetime, then scrambling rates and circuit depths become indirect probes of geometry's appetite for growth. Quantum processors executing chaotic dynamics can in principle measure the speed at which complexity grows toward bounds reminiscent of black hole physics. The most ambitious versions of this program stand distant from engineering's present. Smaller versions already occur in controlled systems, where OTOCs reach the fast scrambling limit associated with horizons. The arrow acquires a computational facet. Even when entanglement saturates, the minimal description length of the state keeps growing, making reversal more than unlikely. It becomes algorithmically forbidding. Instruments also watch the expansion itself. Supernova light curves, improved by better standardization and cross-calibration, baryon acoustic oscillations with longer baselines and finer redshift bins, time delay cosmography in lensed quasars, all refine the Hubble diagram and the equation of state of whatever drives acceleration. Tensions, such as differing values of the Hubble constant inferred from early and late universe data, are treated not as crises but as instruments, way of saying that models need sharpening or that some new ingredient waits in the wings. The arrow's tie to horizons depends on this bookkeeping. A cosmology that changes the future's boundary conditions will change the long arc of direction. The architecture of neutrinos remains a hinge. Underground caverns fill with ultra-pure water or liquid argon to watch faint flashes from ghost-like particles. Oscillation parameters tight. Mass ordering moves toward resolution. The search for CP violation in the lepton sector continues. A Majorana nature for neutrinos, if revealed by neutrinoless double beta decay, would reshape baryogenesis scenarios and alter how early time arrows were set. Even a null result narrows possibilities. Colliders, in the meantime, survey the Higgs sector for self-coupling and rare decays. Any deviation could hint at fields that influenced inflation or the stability of the vacuum, scenarios where a different arrow might have been written. In every domain, the program is the same. Measure what can be measured, lower noise, in large samples, cross-check with independent methods. Ask whether the arrow's apparent universality, its alignment in thermodynamics, radiation, psychology, and cosmology, survives deeper scrutiny or hides small misalignments that point to new law. No single experiment claims the prize. Many together constrain the family of acceptable stories. A past hypothesis without a mechanism must still match the statistical fingerprints in the microwave sky. A geometric constraint on early curvature must speak in the language of polarization and lensing. Inflation, if responsible, must survive the gauntlet of non-Gaussianity limits and B-mode hunts. Holography must map thought to surface without contradicting any ringdom. Quantum thermodynamics must keep its equalities under repeated assault in traps and beams. The tools do more than confirm. They narrow the location of ignorance. Each upper bound on primordial tensors, each precise measurement of structure growth, each pulse arrival time that fits a correlated hum, each successful test of Landwehr's cost, each confirmation of area increase, moves the remaining explanation into a smaller region. What remains is difficult by design. The origin of initial conditions, the status of horizons in a complete quantum gravity, the measure problem in eternally inflating spaces, the emergence of time from correlations without adding it by hand. These are not questions a single mission can answer. They are knots tied across fields, to be loosened by the slow torque of coordinated evidence. The scene, under all this, remains composed. Cryostats hiss softly while superconducting resonators flip qubits with microwave tones. Radio dishes stare at pulsars that keep time more steadily than clocks. Mountaintop cameras chase supernovae across season and sky, and fiber links carry optical phases across continents so that clocks can hear Earth's curvature. In basements beneath mountains, photomultipliers watch for flashes too shy for daylight. On the ocean of the CMB, new boats prepare to launch. In the desert, mirrors tilt toward galaxies whose light began the night humanity learned to count heat. Each instrument bears the same quiet vow, to translate time's direction into numbers that can be compared and equations that can be wrong. The arrow will not be caught by a net of any single mesh size. It is stitched from initial smoothness, gravitational hunger, environmental entanglement, and the economics of information. The tools at hand, the telescopes that read horizons, the detectors that hear mergers, the clocks that weigh potential, the traps that price memory, the colliders that search for tiny asymmetries, turn that stitching into a fabric that can be touched. From this fabric, the remaining pattern becomes visible. It leads next to reflection. What it means, not only that the universe prefers a direction, but that beings exist who can notice it, audit it, and live within its flow. Across the ledger of physics, the arrow appears not as a verdict, but as a habit. Laws preserve symmetries. The world composes histories. In quiet laboratories and among distant galaxies, the same tendency writes itself into matter and memory. Correlations spread, records accumulate, gradients fade. A universe that began in smoothness learns complexity by spending that smoothness, and in the spending discovers narrative. The story is not told by one principle alone. It is told by boundary conditions that denied conspiracy, by gravity that loves irregularity, by environments that take possession of quantum phases, by information that prices each erasure in heat. The arrow is the voice shared by these agreements. Relativity sketches a stage where all events coexist, a block where past and future are coordinates rather than becoming. On that stage, the arrow cannot be a moving spotlight. It must be the pattern of records embedded in the block's fabric. Where records are dense and redundant, what is labeled past acquires the weight of fact. Where records have not yet formed, what is labeled future remains a distribution of possibilities. The alignment of arrows, thermodynamic, radiative, psychological, emerges as a structural property of the block. One side of a low-entropy boundary contains volumes filled with records of earlier states, while the other side does not. In this geometry, becoming is not a separate substance. It is the local tilt of correlations and the direction of inference that observers reconstruct when they read the world. In quantum theory, time enters twice, as the reversible spread of amplitudes and as the irreversible appearance of outcomes. The first respects unitarity, the second seems to break it. Decoherence reconciles the two by changing the question. Amplitudes entangle with uncounted degrees of freedom, and the interference that would reveal reversibility becomes a practical impossibility for macroscopic collectors of evidence. The arrow returns as a bookkeeper's limit. It is not the mathematics that is incomplete. It is the access of any real apparatus, hemmed in by its couplings and its inability to gather the universe into a single calculation. Cosmic horizons make the same point in a different language. Even perfect instruments cannot include what lies beyond a boundary that recedes faster than signals travel. Irreversibility is a feature not only of dynamics but of access. Information theory closes the loop between knowledge and heat. Landor's bound, verified in systems small enough to watch one decision at a time, reveals that memory is never free. The ledger links logic to thermodynamics. Erasing a bit dissipates at least. In that price list, biology and technology alike purchase their clarity. Genomes copy, repair, and forget by paying in gradients. Neurons write and overwrite synapses by exporting entropy. Silicon labors under cooling systems designed to carry away the cost of order. In this economy, the mind's experience of time's passage becomes a thermodynamic transaction. The arrow is painted onto perception because making a present from a cloud of alternatives demands energy and leaves waste. A universe in which nothing could be thrown away would be a universe without narrative. Gravity takes the language of information and writes it on surfaces. Bekenstein and Hawking showed that horizons carry entropy in proportion to area. Holographic dualities refine the hint into a grammar where entanglement and geometry map into one another. In such a dictionary, the growth of extremal surfaces in a bulk spacetime corresponds to the growth of entanglement in a quantum theory. The thermalization of a many-body state looks like the formation of a black hole. The late-time fall of the page curve appears when new saddles, the islands, are allowed in an entropy calculation. Direction becomes geometry's appetite for enlarging wedges of correlation. Even when a global auditor can recover unitarity by counting across a horizon, every local creature experiences the arrow as an increase in ignorance and a proliferation of records on this side of the surface. The world does not lie. It speaks different truths at different scales of inclusion. The question that remains is not a technicality. If the arrow is a tapestry woven from typicality, boundary conditions, coarse graining, and horizons, then the loom is the initial state. A low-entropy beginning allows a million subsidiary laws to line up and point the same way. Why that beginning? Inflation can stretch a patch into a cosmos and carve the statistics of its ripples. It does not remove the need for a patch that was already smooth enough to begin. A geometric constraint like vanishing whale curvature at the birth of spacetime would promote initial simpleness from an accident to a rule, but it still begs derivation from deeper principles. A CPT symmetric or Janus cosmology sets two arrows back to back across a minimal neck. It restores elegance globally while leaving local histories intact and uncommunicating. Each path writes because, in a different handwriting, none yet compels assent. In the distance, the arrow's fate shades into quiet. If acceleration persists, horizons will tighten around island universes of bound matter. Stars will dim and go out. Black holes will evaporate on scales so long that language fails. The background will settle into a thin bath near a de Sitter temperature. The arrow will persist in pockets where gradients can still be found, on the surfaces of cooling remnants, in the slow chemistry of cold dust, in the rare outbursts of a decaying vacuum if nature harbors instabilities hidden from present sight. Farther still, fluctuations may remain as the last agents of change. A coherent cosmology must prevent those fluctuations from populating eternity with counterfeit observers who outnumber those born from stars. The requirement is austere and humane at once. A theory of time's direction must protect the meaning of observation. Meaning enters not as a separate realm, but as a reflection inside the physics already tallied. In a world where records cost energy, life is a machine for arranging order locally by spending it globally. Cultures are echo chambers of redundancy. Libraries, languages, and shared rituals are devices for distributing records so widely that forgetting becomes improbable on human scales. The arrow gives mortality and memory the same root. Both are consequences of a universe that found a way to store facts by letting possibilities collapse into histories. The poignancy of aging and the possibility of understanding share an origin in entropy's slope. The same tilt that erodes makes science accumulate. In that light, freedom becomes a statement about selection under constraint. Laws set the grammar, boundary conditions fix the key, the arrow is the meter. Within those limits, organisms, minds, and civilizations compose. They borrow low-entropy resources, sunlight, chemical gradients, fossil energy, and write local structures whose beauty is the signature of a debt. The repayment is heat, waste, and the quiet insistence of equilibrium. Agency is the art of spending well. Steering flows through narrow channels where small forces leverage large outcomes before dissipation wins. The arrow does not forbid, it prices. On the scale of thought, the arrow gives time depth. Without a direction for records to accumulate, there would be no fossils, no starlight bearing information across millions of years, no geologic strata reading like diaries, no background radiation murmuring of an early fire, no algorithms converging, no archives to consult. The universe would be a restless equilibrium, alive with fluctuations but empty of memory. Instead, it is a place where evidence is cheap to make and costly to purge. That asymmetry is the moral center of scientific method. Claims can be tested because the past is written redundantly, and errors can be corrected because the cost of overwriting small pockets of record is finite even as the global trend toward disorder continues. The arrow grants the possibility of knowledge at the price of heat. There is humility in this arrangement. The maximal description of the world may be timeless, a set of correlations on a manifold or a state in a Hilbert space without a preferred parameter labeled now. Yet beings inside that description possess clocks, molecules that oscillate, hearts that beat, photons that redshift, and those clocks are not illusions. They are subsystems whose correlations with others define an emergent flow. The page, Wooter's picture, demonstrates the logic in microcosm. Conditional states evolve when referenced to a clock, even though the joint state remains fixed. Thermal time extends the lesson. Given a state and the algebra of observables, a natural flow can be defined, and its direction is anchored in the state's asymmetry. Time in this reading is not prior to the world's content. It is a summary of how content relates to itself. The arrow is the sign on that summary. The closing scene is not a resolution, but a composition that holds steady. Ancient light continues to cool, carrying the imprint of a beginning that was extraordinarily simple. Galaxies continue their slow settlement, feeding black holes that hum in ripples of spacetime and glow in rings of polarized light. Laboratories continue to count single quanta and single bits, measuring the costs of knowledge and the price of erasure. Clocks continue to argue with gravity and agree with one another about how deep the argument should cut per centimeter of height. Across these scales, the same direction is honored. It is not a tyrant, it is a consensus. What this means for a species able to notice is also simple. Survival, understanding, and meaning draw from the same spring. Survival is thermodynamic craftsmanship, maintaining low-entropy structures in a universe that offers them briefly. Understanding is the patient construction of records that resist noise. Meaning is the recognition that these labors are not in opposition to nature, but are nature's way of briefly tightening local knots in a fabric designed to loosen. The arrow that empties stars is the arrow that makes first words possible and last words necessary. It writes loss and learning with the same pen. The mystery that began with steam and sharpened beneath horizons remains open where physics meets origin. Why that first page was so blank, so smooth, so promising, why the initial conditions selected a world that could remember, has not yet been answered. The failure is not defeat, it is an invitation. The mathematics already says how an arrow can arise once a special beginning is granted. The instruments already read its signatures in backgrounds, mergers, echoes, and heat. What comes next is not a new commandment, but a better story about the first sentence. Until then, the arrow holds. A leaf completes its fall and does not climb. A star sheds its heat and does not gather it back. A thought becomes a memory and does not unthink itself. The cosmos spends its early order to write structure, sends that structure to write records, and lets those records write beings who can read. The script runs forward not by prohibition, but by preference, not by law alone, but by the sum of conditions that turned symmetry into history. In the stillness between heartbeats, in the hush after a supernova's light reaches a mirror, the same current is heard. A soft insistence that what has been written remains, and what will be written waits on the far side of a boundary that recedes as fast as curiosity can walk.